Okay, great. So it's my great pleasure to welcome Ben Davison again at the seminar, and title of his today's talk is Affine BPS algebras and W algebras. Ben, please.
Okay, thank you very much for the invitation. It's a great pleasure to speak in this seminar again. I'll be speaking about something somewhat related to what I spoke about last time, but maybe something a little bit more concrete. And for me, it's a kind of origin story of where a certain half of an affine Yangian comes from. I noticed when going back through these slides that on pretty much all of the first half of the slides, the title has algebra in it. And I don't want you to worry that this is an algebra talk. Rather, for me, algebras and quantum groups are really only interesting when one has a good handle on their geometric origin, i.e. when they come from nature. So the point of this talk is to show how a certain algebra, which is a quantum group in the sense of being a deformed universal developing algebra, the Lie algebra, how it intrudes into our lives. Okay, so without further ado, as warned, there's just lots of algebra to start with. So in this first slide, let me introduce a half of a certain W algebra. So we start off by considering the ring of polynomial differential operators on the complex torus. And although this has a product, we're just going to consider it as a Lie algebra. We take the commutator Lie bracket on this.
So torus, you mean one-dimensional, just C star?
Yeah, C star. Yeah. Yes, so the Lie algebra W1 plus infinity, there's already something in the chat. Is that just the nodes? I presume that's just the nodes. Okay. Is a one-dimensional central extension of this Lie algebra. The nature of that extension won't concern us today because we leave it out of our half. But this algebra, it contains elements D, which is just Z times D over dZ, and also Z. And one can write down what the Lie bracket is with respect to monomials in these two generators, and it has this particularly simple form.
What's plus what plus refers to? Because you don't have negative powers of Z or what? Or it just...
Oh, yeah. That is right. Yeah, exactly. The plus is there too early. Sorry. So W1 plus infinity is a central extension of this Lie algebra of differential operators. And let me just go forward. So this is where the plus actually should have appeared for the first time. And as you guessed, it comes from the stipulation that M is a strictly positive power. So it's just a half of this Lie algebra. Now we can make this into a graded vector space by simply decreeing that these monomials have by degrees m and 2a minus 2. And I'm making no claim yet that that makes this into a bigraded Lie algebra, because in fact it doesn't. This grading is not fully respected by the Lie bracket, as in fact you can easily verify it by just looking at the formula for what the Lie bracket of two monomials is.
With respect to D, is just a filtration, yeah, like non-differential.
That's right. So for the first copy of Z, we're in luck. Again, just by staring at the formula for the Lie bracket, you see that you have a nice clean power of m plus n here next to the z, so everything's good here. But indeed, with respect to the D, things are a little bit more interesting. And one should say rather that this Lie algebra is only filtered by the second copy of Z, i.e. if we define this filtration in this slightly involved way that I've written here, one gets that the Lie bracket at least respects the filtration. And so if one passes to the associated graded with respect to this filtration, one does in the end get a bigraded Lie algebra. And the only thing to note about it is that because I've been slightly careful about the degrees, i.e. there's this shift by 2 everywhere, the Lie bracket is not 0 in this Lie algebra. And it has this nice form. And this appears in a number of contexts. It appears, for example, as a sort of affine quadrant of quantum torus appearing in work of Kontsevich-Soibelman on motor Victor Thomas theory. It appears in cluster algebras. It appears recently in this paper on the P equals W conjecture by the 4-author group. This is the sort of one relation that appears in the algebra that sort of governs the representation theory there that proves the theorem. But anyway, all I want to note is that this Lie bracket is non-zero, that this is an interesting Lie algebra, or mildly interesting at least. Okay, so that's a bit on W algebras. Probably more familiar, and so more embarrassing if there are typos here too, is the Heisenberg algebra. So Heis will denote the Lie algebra, three-dimensional Lie algebra with generators P, Q, and C, where P is a raising operator, Q is a lowering operator, and C is central, with the three relations that I've written down here. And we say that a Heisenberg module, or module over the Heisenberg algebra, has central charge C, a number in Z, if the central element C acts by multiplication by this constant C. And just some notational terminology, a Heisenberg module is, I'll call it integrable, if we can write it as a direct sum of submodules with central charge in Z. And yeah, so we can give the Heisenberg Lie algebra a grading, and I have a little bit of choice here, but I've decided to put P in cohomological degree 2, C in cohomological degree 0, and Q in cohomological degree -2. And a graded module over the Heisenberg algebra is just exactly what you think it is. It's a module along with a decomposition that is respected by the action of the Heisenberg algebra, i.e. P takes me from the dth summand to the d+2 summand, and Q takes me the other way. Okay, so yeah, so we're guessing here two different sorts of grading are going to appear on graded Heisenberg modules, one by central charge, one by the actual grading, and they will be, somehow fundamentally different. Okay, so there is an action of the Heisenberg algebra on this half of W1 plus infinity, and if I fix the exponent of Z and take the span of Z to the A, D to the M for M all numbers, this is an irreducible representation of central charge 2A. What's more, this Lie algebra, sorry, I should write Lie algebra object in Heisenberg. This Lie algebra is a Lie algebra object in the category of modules over the Heisenberg algebra. That is to say, there is a tensor product of module. There's a tensor structure on the category of modules over the Heisenberg algebra, where the tensor structure takes a pair of modules, takes the tensor product of the underlying vector spaces, and lets the Lie algebra act via the sum of the actions in the two components. And one can check that the Lie algebra bracket in W1 plus infinity is a morphism of modules over the Heisenberg algebra.
And the action is a natural one, yeah, you realize P and Q, like.
Yeah, I at the last moment decided to actually include it. So P is, yeah, the Lie bracket by D squared, and Q only looks at the kind of D components and replaces a polynomial in D by the derivative of that polynomial, again evaluated on D. And it's an easy exercise to check that this makes this this span of monomials with the exponent of Z fixed at A into a module of central charge 2A. And it's somehow obviously irreducible because I can get all of these via from z to the a, d to the 0 via iterated Lie bracket with d squared. Okay. So yeah, just to reiterate, because I didn't write the word Lie in the slide, W1 plus infinity plus is a Lie algebra object in this category. And if I pass to the associated graded, I guess Lie algebra objects in the category of graded modules over the Heisenberg algebra. Okay, so I've decided to give these irreps that appear in W1 plus infinity a name. So
I'm having a bit of trouble with this P of D. P is the element in the Heisenberg Lie algebra.
Oh,
yes.
Yeah, sorry. Yeah, okay. Yeah, that's just a horrible typo.
So you were thinking P is just any polynomial of D inside of the W algebra, right?
Yeah. P is a polynomial.
P is not equal to P. Yes.
And the P prime is actually the derivative of the polynomial with respect to D. Am I right on the right hand side?
Yes.
Okay. Yeah. Thank you.
Yeah. Thank you very much for pointing that out. That's extremely confusing. Okay, so I've given these irreps that appear inside W1 plus infinity a name. So V subscript B is the graded lowest weight representation that appears in W1 plus infinity with central charge B. And then the A is a possible cohomological shift. So recall that I put the monomial z to the m d to the 0 in cohomological degree -2. So the vacuum vector, if I don't shift this module, sits inside degrees -2. So if I then do shift by a, I get the shift that you see here, that the vacuum vector appears in degrees -a, in degree -a, -2.
What do you mean when you say cohomological degree? So far, it's kind of pretty abstract.
Yeah, it's so that extra grading degree I think of as cohomological degree. So I think of graded modules as cohomologically graded, just because I'm going to end up matching them with things.
Why do you call it cohomological? Apparently for no reason.
For reasons that will become clearer
later. Okay.
Later. Yeah. Yes. Okay. So because of the way I've set up the degree shifts, I hope I've got this right. Yeah, I've got this right. The associated graded of this W plus Lie algebra is the direct sum of all of these V's, but with no cohomological shift, so no A shift appearing in this direct sum. And what's more, and this is not at all difficult to show, but somehow fundamental, this is the universal algebra object that contains a copy of V2, or the universal Lie algebra object, I should say, that contains a copy of V2 and also contains no shifts of any of the V2Ms. So the way this looks is if I just take the free Lie algebra object generated by V2, I get something much bigger than W plus 1 plus infinity. But it's bigger because it contains a whole bunch of cohomological shifts of these V modules. And if I just throw them all out, i.e. quotient them all out, then I wind up with the associated graded of W1 plus infinity. So it's universal in the sense that if I have any Lie algebra object in the category of graded modules over the Heisenberg algebra that happens to contain V2 and doesn't contain any shifted copies of V2Ms, then I have a unique morphism from this associated graded into that module that takes the copy of V2 sitting inside of here to the copy of V2 that I've already identified. So it satisfies a universal property in the usual category theoretic sense. Okay, so that's some just a lot of algebra. And here's some more. So So let Q be a quiver, which is algebraists speak for a directed graph. I.e., we have a set of vertices, a set of edges, which are denoted Q0 and Q1 respectively, and two morphisms, S and T, standing for source and target, taking an arrow or an edge to its source and its target. So this is really just a combinatorial gadget, a directed graph. And I allow loops, I allow multiple edges, I allow really anything, but I will require that both these sets of edges and vertices are finite. I denote by CQ the free path algebra of Q over C. So this has as a basis over the complex numbers paths in this directed graph, including paths of length 0, starting and ending at each vertex I. And then multiplication with respect to this basis is just given by concatenation of paths, if the paths will concatenate. But if I try and multiply a path that ends at a point that is different to the point that a different path starts at, then their product is 0. So hopefully that will be somewhat familiar to any people in the audience. I take, and this should be a quotient. So I take W in CQ quotiented by the vector space spanned by commutators in CQ. So really this is just a linear combination of cyclic paths in my quiver. If A is an arrow in my quiver and W is a single cyclic word or a single cyclic path, then one defines the hang on, this just really annoying me. There we go. That's a quotient sign. I've somehow managed to make it look worse. Yeah, so if A is an arrow and W is a single cyclic word, then we define the non-commutative derivative of W with respect to A like so. We cyclically permute every instance of A to the front of this cyclic word and then delete it. And then for arbitrary W, we extend by linearity. Fine. Then the Jacobi algebra is defined to be the quotient of the free path algebra of Q by the two-sided ideal generated by all of the non-commutative derivatives. I'm not sure how much sense that makes without an example. And luckily for this talk, we really only need one example. So Q1 is the quiver with one vertex. And sorry, this is what happens when you change your notes at the last minute. This should be a 3. So Q3 is the quiver with one vertex and 3 loops, which I denote A star, and omega. And my potential is going to be omega A star minus omega A star A. Okay, so if I want to take the non-commutative derivative of that with respect to omega, then I cyclically permute omega to the front of each word it appears in and then delete it. And that way I just get A star minus A star A. So I get the commutator of A and A star. Likewise, if I want to take the non-commutative derivative with respect to A, I cyclically permute A to the front of every word and delete it. And that way I get A star omega from the first word minus omega A star from the second word. I get the commutator of omega A star. And so putting the 3 relations together, I get the free path algebra is just the polynomial algebra in 3 non-commuting variables. Whereas when I impose the relations coming from the Jacobi algebra presentation, I impose the commutators of those 3 pairs of elements in this algebra. And so I get the Jacobi algebra is the free polynomial algebra in 3 variables in the usual commutative sense. How do I get rid of this? Good. Okay. Okay, so the way I'm going to build quantum groups is by considering what are called cohomological Hall algebras. So these are certain structures put on top of the cohomology of moduli spaces of objects, or moduli, in this instance, it will be moduli spaces of modules for Jacobi algebras. So let me construct those moduli spaces for you. First, I fixed D a tuple of numbers indexed by the vertices of my quiver. So I should mention that if I have a representation of this free path algebra, recall that in the free path algebra, I had these what are called lazy paths of length 0 at each of the vertices, which I called EI. If I let EI act on my representation, I get a vector space, which you can think of as the vector space that sits above that vertex, and the arrows as being morphisms between these different, or being centimorphisms between these different vector spaces. So then it's not a giant leap to see that this big affine space of homomorphisms from copies of C of dimension, whatever the dimension vector assigns to the source of an arrow A, hom to C to whatever the dimension vector assigns to the target of A. This gives me a family of d-dimensional CQ modules. I'm somehow overcounting in that there are modules at different points that are isomorphic, considered as modules for the path algebra. But it's not hard to see that that overcounting is exactly accounted for by taking orbits with respect to a certain gauge group. So that gauge group is, I'm going to denote it GLD, and this is the products over the vertices of essentially the automorphism groups of the vector spaces I'm assigning to the vertices. And the statement is that 2 points in this A space correspond to isomorphic CQ modules, if and only if they lie in the same orbit. And so at a slightly higher level of technicality, one can show, or one can simply say, that the stack of d-dimensional modules for the path algebra of Q is given by this quotient in the stack theoretic sense. So if you don't like to think too hard about stacks, it's not so much of a problem. Let me just say 2 things. Firstly, that what this space does is, well, the points of this space are what you want them to be. They are isomorphism classes of CQ modules. But the point is that these points come with automorphism groups, and the automorphism group assigned to a point in the stack will be the automorphism group of the representation corresponding to that point. The second thing I want to say is that if you'd really rather not think about stacks, that's not so much of a problem here, because I'll be taking the cohomology of this thing, and by some sort of fairly formal yoga, the cohomology of a global quotient stack is simply, let's say, the quotient of A by G is simply the G equivariant cohomology of A. So wherever you see cohomology of a stack, you can really think of equivariant cohomology of something more concrete, as varieties say. Okay. Having said that, I'm just going to liberally use the language of stacks throughout the rest of the talk. So recall that the Jacobi algebra assigned to Q and W is a quotient of the free path algebra of Q. So representations, or the stack of representations, the Jacobi algebra naturally sits as a substack of the stack of representations of CQ, i.e. those representations that obey the relations coming from the non-commutative derivatives. On the other hand, this element W is an element of the free path algebra, at least up to taking commutators. And if I have any element of an algebra, this gives me a function on the stack of modules, on any stack of modules for that algebra, defined as follows. If I have any representation, I can evaluate my elements of the algebra on that representation to get an endomorphism of the underlying vector space, take the trace of that endomorphism, and that gives me a function. Okay, so the statement is that considered as substacks of this smooth ambient stack of representations of the free path algebra, there is an equality between the stack of representations of the Jacobi algebra and the critical locus of this function. And this is an important geometric fact. Okay, so finally, I believe in this slide, I get as far as actually defining or at least indicating how to define the what's called the critical cohomological Hall algebra. And in the title of the slide, I've called it the 3D cohomological Hall algebra. And that will be because it has something to do with 3D algebras. So we'll find that in our running example, the Jacobi algebra, well, we've seen that in our running example, the Jacobi algebra of the 3-loop quiver with its canonical cubic potential is the polynomial algebra in 3 variables. And so if I look at representations of that, let's say finite dimensional representations of that, I'm really looking at coherent sheaves on a 3-dimensional space. And that's the sort of general feature of this story, that there's a kind of 3-dimensionality to it, hence the 3D in this title. Anyway, given the data of a symmetric quiver, so by symmetric I mean between any 2 vertices I and j, there are as many arrows going from I to j as from j to I. And that's just that's somehow an important thing for me to mention, for me to make what I'm about to say all true. But were it to fail, there's a way of modifying what I'm about to say to make it continue to be true, but I just don't want to go into it because I don't need to. All right, so given a symmetric quiver with potential W, we define the critical cohomological Hall algebra, which will be a graded thing. It's graded by dimension vectors, following the definition given by Kontsevich-Soibelman some years ago. So each graded piece is given by, so first we take the stack of representations, d-dimensional representations of the free path algebra, and instead of considering the constant sheaf on it, we consider what's called the perverse sheaf of vanishing cycles for the function trace W. So it's kind of clear that we shouldn't take the constant sheaf, because if we do, we're not incorporating the data of W at all. But it's perhaps less clear why we don't take, say, the constant sheaf on the stack of representations of the Jacobi algebra. There are myriad reasons for that. It doesn't give such a nice theory, and somehow the sheaf of vanishing cycles is a more deformation invariant thing. So it enables us to kind of import ideas and intuitions from Donaldson-Thomas theory. But for the purposes of this talk, I'll justify taking this sheaf by the fact that it gives the right answer, that it, you'll see at the end of the talk that it gives a nice answer. Okay, so without defining the sheaf, let me just say that it's something that measures how singular the function trace W is. So at a first level of approximation, it's only supported at the critical locus of this function, i.e. it is only supported on the stack of representations, the Jacobi algebra. So if you like, you can just think of it as a sheaf on the stack of representations, the Jacobi algebra, and you get the same thing if you then go ahead and take its derived global sections, as I've done here. Okay, so then we play the usual game that we always play when defining Hall algebras. We take the stack of short exact sequences of CQ modules. A short exact sequence has 3 entries, and so I have 3 projections out from this stack into the stack of all modules, given by just remembering those 3 entries. And there's a somewhat standard correspondence diagram that we can consider here, where the map going left takes a short exact sequence and just remembers the extremal terms, and the map going right remembers the middle term. And I've written it in a sentence, of course, in the paper, and in real life, it takes more than a sentence to check that this makes sense, can be defined, gives an associative product, and all the rest of it. But as time is finite, I put it in a sentence. We define the multiplication on the cohomological Hall algebra via pullback and push forward operations defined by the morphisms in this correspondence diagram. We first pull back along pi1 cross pi3, and then we push forward along pi2 to get a morphism from the vanishing cycle cohomology of the thing on the left, 2 copies of the stack of representations of CQ, to the vanishing cycle cohomology of CQ. And like I say, I've left out a huge number of details here, but maybe one that I can't get away with leaving out is that embedded in this definition is also the Tom Sebastiani isomorphism, which is a kind of Kunath isomorphism for vanishing cycle cohomology, which, yeah, anyway. So, yes. So there are a number of things here which are sort of under the hood. One is, I haven't really given you a definition of the vanishing cycle perverse sheaf, and that I'm going to be able to justify in a slide or two's time via something called dimensional reduction, which is a way of taking a space with a vanishing cycle complex on it and showing under certain nice circumstances that the derived global sections of that sheaf are given by the dual compactly supported cohomology of a constant sheaf on some other space. So it's some way of getting rid of vanishing cycles from the story, which will mean that it's somehow slightly less egregious for me to not give you the definition. Okay. So, like I say, I'm really only interested in algebra and algebra actions that come from geometry. So, luckily for me, there is a geometrically defined action of the Heisenberg Lie algebra on the cohomological Hall algebra for any quiver and any potential, which somehow only really uses well-known constructions, but it's fairly neat nonetheless. So there is a morphism from the stack of all modules that takes a module rho to just the determinant of the or the top wedge power of the underlying vector space of rho. And this makes sense in families, so it gives me a morphism from the stack of representations to the to BC star, i.e. the stack point mod C star. So this gives me an action of the cohomology of BC star, which is just a polynomial algebra in one variable u sitting in cohomological degree 2. So this hopefully begins to answer Jan's question as to why I kicked off by calling the grading as the cohomological grading. Yeah, so this defines an action of QU via pullback in vanishing cycle cohomology along this map. So I have a map from the stack to BC star across the stack that is just det in the first, there should be no I here, det in the first component and the identity in the second. And my raising operator will just be the action of the generator U. So that's that also explains why I insisted on putting my raising operator in cohomological degree 2 in order to match up with this. Going the other way, there is an action of BC star itself on the stack. So if I have a module or even a family of modules and I have a line, i.e. a one-dimensional vector space, I can tensor them together to get a new module, and that gives me an action. Yeah, so this, yeah, so there's a morphism from BC star across MDCQ back to MDCQ, and this defines coaction. If I take cohomology, I go from cohomology of MDCQ or vanishing cycle cohomology of MDCQ to vanishing cycle cohomology of BC star across MDCQ. And we obtain a lowering operator as follows. So if I have some element alpha inside the CoHA, I can apply this coaction to it, and I get some formal power series in U to the n with coefficients in the CoHA itself. And I just pick out the linear coefficient, this alpha 1. And that likewise drops my cohomological degree by 2, again, because U itself has cohomological degree 2. And
why the commutator is central?
Oh, I mean, that takes a little bit of work. It's not completely
So
obvious.
it's a computation, yeah. Okay.
It's a computation, yeah. Yeah. So I should say I just let C act by multiplication by the central charge here, and then it's a computation that is a well-defined action of the Heisenberg Lie algebra, but it's not super difficult. And furthermore, one can show that the algebra structure on the cohomological Hall algebra itself respects the action of the Heisenberg Lie algebra. So put more succinctly, maybe the cohomological Hall algebra AQW, and this is with no constraints on what Q and W are, is an algebra object in the category of graded modules for the Heisenberg Lie algebra. Okay. Yeah, and that's all I want to say about that. So as promised, I'm going to give you a way to sort of get rid of vanishing cycles. So let me start off with some definitions. So if I have a finite quiver Q, we define the doubled quiver in the usual way by adding, for every arrow A, we add an arrow A star with the opposite orientation. And the pre-projective algebra is the free-path algebra of this doubled quiver modulo the two-sided ideal generated by the sum of the commutators. So that's a kind of 2D thing it will turn out, as we'll see in the running example. So we define the tripled quiver by just adding a loop omega I at every vertex of the doubled quiver. And then this carries something called the canonical cubic potential, which is the sum over the vertices of these new loops times the sum over the arrows of the original quiver of the commutators AA star. And it's an easy exercise to check that there is an isomorphism from the algebra, the polynomial algebra in one variable with coefficients in pi q to the Jacobi algebra of q tilde w tilde, and it sends omega, the central element, to the sum of the loops appearing in the tripling construction. Okay, so here, as promised, is a way to get rid of vanishing cycles from our lives for the rest of this talk. The dimensional reduction isomorphism is, I mean, it's a general geometric fact, but it yields the following isomorphism between the vanishing cycle cohomology with a tripled quiver with its canonical cubic potential. This is isomorphic to the Borel-Moore homology, which is really the dual compactly supported cohomology of the stack of representations of the pre-projective algebra, with a certain cohomological shift, which just depends on the combinatorics of Q. And I should say in our running example, there will be no shift, so I'm not going to define it. So in our running example, where Q is the one loop quiver, if we double it, then it becomes the two loop quiver with loops A and A star. And then when we take the pre-projective algebra, we impose the one relation that A and A star commute. So the pre-projective algebra is just the free polynomial algebra in two variables. And we've already seen that the Jacobi algebra is the polynomial algebra in three variables, which conforms to this fact in the first bullet point. And so via dimensional reduction, i.e. via this isomorphism capital phi, we can sort of transport the Kontsevich-Soibelman cohomological Hall algebra structure from the left-hand side. Theirs is an algebra on vanishing cycle cohomology. We can transport it to the right-hand side. And here, representations of this pre-projective algebra, because it's a commutative algebra, is really the same thing as looking at compactly supported coherent sheaves on the spectrum of that algebra, i.e. on A2. So we're just looking at sheaves on the plane.
And this, you see, there is something which kind of I always did not like. This A2 is a very specific coordinate plane in A3 when omega equal to 0.
Yeah. There's a symmetry breaking here, which which I also am not a huge fan of. But
Okay.
Okay. So for an arbitrary quiver with potential, one thing I want to say straight off the bat is that this algebra is huge. I mean, even if I fix a dimension vector, as long as that dimension vector isn't 0, the cohomology, the critical cohomology, is not only very hard to calculate, but also infinite dimensional. But the integrality theorem, or any cousin of it, tells us that, okay, the thing is huge, but it's generated in some fairly straightforward and easy to write down way by something that is graded finite dimensional, i.e. something that such that each piece graded by a dimension vector is itself finite dimensional. And the following theorem is an example. So the theorem says that there's a natural subspace of the cohomological Hall algebra, which is closed under the commutator Lie bracket, such that this morphism gamma is an isomorphism. And I should also say that GQW, its graded pieces are finite dimensional. And here the Q adjoined U is acting in the way that we've already seen via this raising operator P, i.e. via the action of tautological classes. So if I have an element in GQW tensor QU, I can, because GQW sits inside the cohomological Hall algebra, I can get out of that tensor an element in the cohomological Hall algebra. Then if I have a symmetric tensor of elements in the Hall algebra, I can just use the Hall algebra to evaluate it to a single element in the Hall algebra. And that's how this morphism gamma is defined. So it's the usual definition of a PBW type isomorphism. And the theorem joint work with Sven Meinhardt is that indeed this morphism is a isomorphism. And so we define this NQ0 graded subspace. We call it the BPS Lie algebra.
Ben, I somehow maybe missed. You're talking about in general, yeah? So this gamma is isomorphism of what?
Yes, it's an isomorphism of graded vector spaces.
Okay, not as algebras, just in case.
Yeah, as in the case of the classical PBW isomorphism, and I should have mentioned this, thank you. As in the case of the classical PBW isomorphism, unless you pick an especially boring Lie algebra, this will not be an isomorphism. And that's somehow where all the fun is, that AQW is not commutative. It's got a more interesting structure. And we'll see that a bit later in our running example. Okay. So I've told you that there is a natural subspace of the cohomological Hall algebra that has all of these amazing properties. I've not really given you much of a definition. That's because it would require a digression on perverse filtrations and all the rest of it. And even if I were to get to the end of that digression, you'd probably get to the end of it and think, well, that all sounds fine in principle, but absolutely impossible to ever calculate. So the point of this slide is that in the cases that we care about, I tripled quivers with their canonical cubic potentials. We do have actually quite a good chance of being able to calculate what the BPS Lie algebra is. So the sort of first thing that one might wonder about this Lie algebra is how big is it? Or more precisely, what are the dimensions of its cohomologically graded pieces? So here on the left-hand side, I've got the characteristic function of the dth graded piece of my BPS Lie algebra, where the I is keeping track of the cohomological degree that this thing inherits from the cohomological grading on the CoHA itself. So this is a precise formula for what that characteristic function is, given in terms of something from combinatorics, defined by Victor Katz in the 80s. So here, AQDQ is what's called the Katz polynomial, and its definition, and it's a definition / theorem, that it is a polynomial such that if I evaluate it at Q prime power, it returns the number of isomorphism classes of absolutely indecomposable modules over the path algebra, now not with coefficients in C, but with coefficients in FQ. So that's why I had to pick Q to be a prime power, where indecomposable means what you think it means. It means that it can't be written as a direct sum, and absolutely indecomposable means it remains indecomposable even if I pass to the algebraic closure of FQ. So it's a purely combinatorial gadget. It's a beautiful theorem that in fact this counting function is a polynomial, and then it's a string of surprises that this polynomial, which really comes from combinatorics, governs the graded dimensions of this BPS Lie algebra. So
yeah, but Katz's conjectures about usual Lie algebras, it's also this type of result.
Yeah, so so there's more I could tell you about the BPS Lie algebra, which I just didn't put on the side. But one other thing I can tell you about it in order to help you, have some idea what it is that the 0th graded piece of the BPS Lie algebra, at least if we exclude loops from the picture, the 0th graded piece is isomorphic to the Katz-Moody Lie algebra associated to Q. One of Katz's original conjectures was what's called the constant term conjecture, that the constant terms of the Katz polynomial record the dimensions of the graded pieces of the Katz-Moody Lie algebra associated to Q. So yes, again, yeah, you see that here. You see that comes out from this this story. Okay, so if we return to our running example where we started off with the one loop quiver, then it's not too hard to show that for any d, i.e. for any dimension of representations of FQQ, which is really just the polynomial algebra in one generator, A, our starting loop, the number of absolutely indecomposables is Q, i.e. the cardinality of the field itself. And this is independent of D. So using the theorem, that tells us that for every D, the dth graded piece of the BPS Lie algebra for the three loop quiver with its canonical cubic potential is a copy of Q sitting in cohomological degree -2. So now if I take the characteristic function of this, let me skip forward, of this BPS Lie algebra, I get the following.
Characteristic function is what is written in the
Yeah,
lecture.
so that's why I skipped forward, because I thought it would be confusing without including the thing in brackets. So here Q is keeping track of cohomological degree, and that's why everything, the only powers of Q that are appearing have exponent -2, and T is keeping track of the degree by this little d. So for every d greater than or equal to 1, I have a one-dimensional vector space sitting in cohomological degree -2. So when I look at the characteristic function with respect to the bi degree given by cohomological degree and also dimension vector degree, I get this formal power series.
And so from this, you can see the McMahon if you go to this cohomological whole algebra as well.
Yeah, that's true. Using a little bit of wall crossing and using this fact, you can get the McMahon partition function counting 3D partitions. Yes. But okay, so I'm getting towards the end of my allotted time, so I better sew this up. I build a bridge from this CoHA and from this DT theory to the algebra I started with, this W plus 1 plus infinity. Okay, so it's clear that I still have a little bit of work to do, because the characteristic functions of these two things don't agree. The first function is really giving me the characteristic function of all the lowest weight vectors of this thing considered as a modulo over the Heisenberg Lie algebra, but I'm missing this 1 minus q squared to the -1. And if I just skip back, you might imagine, and you'd be right to imagine, that this extra 1 minus q squared to the -1 is coming from the fact that in this gamma map, there's a copy of QU included. Okay, so sorry, skipping back again. One might think, well, okay, so what's gone wrong here is that he should have considered the Lie algebra GQW tensor QU, but there are a few things wrong with that. Firstly, for arbitrary quiver with potential, that thing might actually not be closed under the commutative Lie bracket. And secondly, one has to be careful with the Lie algebra structure anyway. But okay, let me just get to the correct statement. Okay, so we've got a little bit more work to do. And the way to get there, the way to cover the gap is to introduce co-products on the cohomological Hall algebra of a tripled quiver with potential. So let Q be a quiver assumed finite as always. Let UI for I equals 1 or 2 be disjoint open balls in A1. And we consider the analytic substack of representations of the Jacobi algebra, which, recall, was isomorphic to the polynomial algebra in one variable with coefficients in the pre-projective algebra. We let this be the substack such that the generalized eigenvalues of the operator given by omega on whatever module we're considering, those generalized eigenvalues are in this open ball UI. And I'm just going to denote by phi. Phi will always be the restriction of the vanishing cycle sheaf, just to ease the notation a bit. So two things I claim not super hard to show. This one is genuinely easy to show, that if I take the restriction map in vanishing cycle cohomology from the full stack to the stack where the generalized eigenvalues have to live in this open ball UI, then this is an isomorphism. That one is not too hard. The second one is harder, but still just a matter of sitting down and doing it. The claim is that there is an isomorphism between, so here on the left, I take the stack where the generalized eigenvalues all live in the union of U1 and U2. The claim is that the vanishing cycle cohomology of that stack is isomorphic to the tensor products of the corresponding stacks for U1 and U2. I can explain in words why this is highly believable. It's because if I have a module for this algebra, pi q adjoined omega, where all of the eigenvalues for omega are in U1 or U2, then because omega itself is central, if I take, I can take the direct sum decomposition into the generalized eigenspaces for omega. There's a sort of coarse version of that where I just take one summand where all of the generalized eigenvalues are in U1 and the second summand where they're all in U2. Because omega is central, that decomposition is respected by the action of everything else in pi q. So at the level of stacks themselves, the stack of representations where the generalized eigenvalues are in U1 and U2 is the Cartesian products of the stacks where they're all either in U1 or all in U2. So yeah, one still has to do a surprising amount of work to go from that observation to an actual isomorphism, but it's not crazily hard. And these two facts together yield a co-commutative coproduct because I can restrict from the full stack to the stack appearing on the left-hand side of bullet point 2, and then I can use bullet point 2 to get the vanishing cycle cohomology is isomorphic to this tensor product. And then I can use bullet point 1, sort of going the other way, to argue that the tensor product appearing on the right-hand side of bullet point 2 is the tensor product of the CoHA with itself. So in this way, I get a coproduct, and it's somehow obviously co-commutative because in the choice of U1 and U2, I can continuously vary it without really changing anything. And in particular, there's a path whereby I swap the roles of U1 and U2. So then via the Milnor-Moore theorem, that tells me straight away, without really any further work, that the critical CoHA is the universal enveloping algebra of some Lie algebra. And we already know how big the critical CoHA is. The size is given by the symmetric algebra generated by GQ tilde W tilde, the BPS algebra, tensor QU. That came from the PBW theorem. So the size of whatever goes in here, the size of whatever I take the universal enveloping algebra of, has to be given by the right-hand side of this isomorphism, which is good because that's the size of this W1 plus infinity algebra. This QU is kind of giving us the missing factor in the characteristic function. And we've shown that indeed this bigger thing, this GQ tilde W tilde adjoined U, has a Lie algebra structure. And I need to say, in case I forget or in case it's not clear, that the Lie algebra structure will almost never be just the QU, just given by the Lie algebra structure on GQ tilde W tilde extended by a QU linearity. That is, it can have even if GQ tilde W tilde is abelian, this Lie algebra might fail to be abelian. And that's exactly what happens in the case that we consider.
So,
Okay.
but this is some kind of affinization of what? How should I think of this procedure?
I think of it as an affinization. I call it an affinization. I'm still undecided as to whether that's a misnomer. But just at the level of generating functions, it looks like some kind of affinization.
Although it's not affinization in the very strange. Yeah, it's a bit funny. Yeah, it's not a linear extension, not just a linear and central extension, but it's some strange construction.
Yes.
Yeah,
I possibly shouldn't call it this, but
Yeah, no, maybe it certainly looks as an affinization. By the way, this introducing this dependence on the open set on the line, it seems to make this homology inter factorization algebra.
Precisely. Yeah, exactly. Yeah, exactly. The full statement is that well, if I try to say it now, I'll get it wrong. The full statement is that what we have here is an algebra object in the category of factorization sheaves on the configuration space of points on A1.
And by the way, if I remember, I forgot who, maybe Kevin Costello, who proved that there is a corresponding vertex operator algebra.
Yes, and I should say also, because it's not written here, that the idea for constructing a coproduct this way is due to Kevin Costello. This is the story here is that he told me how to do it. I went away and checked that it actually works, but then actually writing a paper out about it is somehow beneath Kevin's pay grade, and so that's why it's happening this way. Okay. Okay, so we now have enough to explicitly describe this algebra A2. So remember, this is the CoHA for the 3-loop quiver with its canonical cubic potential. So let me write GA2 hat to be the affinization of this, this affine BPS Lie algebra. Then, as observed, the characteristic function. Oh dear, that should be a hat. It has to be a hat. There we go. Yeah, the characteristic function of this affinization matches the characteristic function of the W algebra. But these Lie algebras are different. So the left-hand Lie algebra is honestly bigraded, whereas the right-hand Lie algebra carries one grading and a filtration. So yeah, they really belong to different categories somehow. But going back to old results of Lane and Nakajima, we can at least show that this GA2 is spherically generated, i.e. it's generated by its summand corresponding to dimension vector 1. But then because these characteristic functions are the same, and by the universal property of the associated gradient of the W algebra, this is enough to show that there is an isomorphism of Lie algebras between this affinize BPS Lie algebra and the associated gradient of the W algebra. And thus, because the CoHA is just the universal enveloping algebra of the affine BPS Lie algebra, we get the following isomorphism of algebras. And in particular, using this and the spherical generation of GA2, we get that the CoHA is spherically generated, which becomes important shortly. And now I have to do this. Okay, so I promised you something about quantum groups. So in the last couple of minutes, let me speed you in that direction. So there are a couple of copies of C star acting on A2, obviously, by scaling the 2 coordinates. But let's just start with a 1-parameter deformation, acting on A2 with the weights 1, -1. And in the 3D model, remember, we think of these arrows that are left over as being coming from the arrows AA star, where we've dimensionally reduced along omega. And in order to promote this to an action on the potential that doesn't scale it, we give omega weight 0. So the trace of A star omega has weight 0, i.e. it's invariant under this C star action. That enables us to promote the construction of the cohomological algebra to something in C star equivariant cohomology. And so, yeah, we just take as the d graded piece, the C star, the derived global sections of the C star equivariant vanishing cycle sheaf on this stack. And using purity, in fact, one can show that this is a free module over the cohomology of BC star. where this BC star isn't the BC star that appeared earlier in the definition of the raising operators. It's really a sort of deformation parameter that's playing a completely different role. But anyway, this is this algebra with the C star added in is now a it's really a sort of flat family of algebras over the affine line, such that if I specialize t equals 0, I recover the original CoHA. So crucially, because of the way I've been quite careful about the weights, recall that the way we got the coproduct structure was by just remembering the generalized eigenvalues of omega. And because I've been careful and made sure that C star doesn't scale omega at all, this morphism that sends me to my generalized eigenvalues, I've still got it. It's C star invariant. So I can run basically all of the same arguments again to show that I've got a co-commutative coproduct. But now everything is happening in this category of QT modules. And by Milner-Moore, again, I get that now this deformed CoHA is the universal enveloping algebra in the category of QT modules of some QT linear algebra, which I've written G hat C star A2, which will be a deformation of the usual BPS Lie algebra. And so why would one look for this? Well, one would look for this if one was slightly disappointed by the result that appeared on the previous slide. We started off the talk by introducing this interesting W1 plus infinity algebra. And on the previous slide, we saw that the affine BPS Lie algebra isn't it. It's something that carries less information, something a bit rougher, i.e. the associated graded with respect to some filtration. And one would be tempted down this route if one were to say, well, where's my BPS Lie algebra that really gives me W1 plus infinity? And one gets it this way. So one can show that there is an isomorphism of QT linear Lie algebras between this deformed Lie algebra and the Riesz construction applied to W1 plus infinity. So if you haven't seen it before, I've written it out explicitly. It's the thing on the right hand side here. The crucial thing here is this is a QT linear Lie algebra such that if I evaluate t equals 0, I get the associated graded Lie algebra. And if I evaluate t any other number, I get the original W1 plus infinity algebra. So it's a kind of deformation of the interesting algebra to the slightly less interesting algebra. And that's what this deformed affine BPS Lie algebra is. And so in particular, that tells us what the CoHA with this extra equivariant parameter is. It's the universal enveloping algebra of the Riesz algebra of W1 plus infinity. And now finally, I realize now I'm out of time. So of course, there is a full 2 torus that acts on A2. And one might ask, well, what happens if we go ahead and do that? Let that act. So one thing that goes wrong is that there's no way to let that 2 torus act in such a way that we don't scale the omega arrows somehow or other. So now the morphism that simply remembers generalized eigenvalues of the omega operator is no longer invariant for t, but that somehow makes it more interesting. That says that we no longer have universal enveloping algebra. We no longer have something with a co-commutative coproduct, but we're looking at a deformation of it. So according to Drinfeld's original definition, that really is the definition of a quantum group. Now, one can show that this now 2-variable deformed CoHA embeds into a certain shuffle algebra, and this is used by Rapčák-Soibelman, Yang, and Zhou to show that the spherical subalgebra generated by there should be a 1 here, by the first part of this CoHA is isomorphic to the positive half of the affine Yangian, a certain quantum group. But along the way, we've shown that this algebra is spherically generated. It's generated by the bit corresponding to dimension vector 1. So it's a sort of, a slight improvement of the Rapčák-Soibelman Yang and Zhou theorem, or a corollary of it and spherical generation, is that in fact, the affine Yangian, or 1/2 of it, which in the literature is presented by sort of generators and relations, really is just the fully equivariant CoHA of coherent sheaves on A2. up to isomorphism. And yeah, that's a good place to finish. Thanks a lot for your patience, and I'll take any questions.
Yeah, thank you very much. And we proved some kind of weaker version of this, yeah, because
only slightly, just that the spherical subalgebra is isomorphic to the affine Yangian. So once you've shown that it's spherically generated, it's obviously immediate.
By the way, your Heisenberg algebra action, which kind of I didn't know, it toward the end it somehow disappeared from
it disappeared. So its role in the story is maybe slightly buried. So it's here. So in order to show that the affine BPS Lie algebra is isomorphic to this associated graded, I've used the Heisenberg action to because these, if all I know is that these are Lie algebras and they have some enormous bigrading, then in principle to show that they're isomorphic is a lot of work, a lot of different checks, infinitely many different checks. But if I know that they are both Lie algebra objects in the category of modules for the Heisenberg Lie algebra, that already makes life a lot easier. It sort of reduces the number of checks that need to be done. But then there's this observation, in fact, that the right-hand side here, this associated graded, has a universal property. Namely, it contains its spherical part, either part corresponding to dimension vector 1 or the part corresponding to monomials z to the 1 d to some power. And it's universal in the sense that if I have any graded Heisenberg, any Lie algebra objects in the category of graded Heisenberg modules, which only contains unshifted copies of these lowest weight representations that appear in the W algebra, then there's always a morphism from the W algebra into that module, which sends the copy of, I was calling it V2 earlier, so the spherical part of W1 plus infinity to the chosen copy of V2 sitting inside my Lie algebra. So that tells me that I have a morphism from the W algebra into the left-hand side. But then because the left-hand side is spherically generated, it's surjective. And then from previous slides, we have the generating functions are the same. So
by the way, you have this in our paper with Rapčák, Yang, and Zhou, we constructed some action of vertex algebras and vertex operator algebras, but can you probably you can define intrinsically those vertex algebras in terms of BPS Lie algebra?
I think so. I think what in this talk or in the paper that I wrote, there's sort of a failure to take advantage of like a very strong hint, which is in this slide, in the second bullet point, in the construction of the lowering operator. I've taken some interesting structure that this whole algebra has, i.e. this coaction of Q adjoined U, which looks an awful lot like it's meant to be part of a vertex algebra description here. And I've thrown away all but one of the modes here. I've just taken the linear one in order to get my lowering operator. I think there's something here. I think there's something here. So, and I'm not quite sure what you're supposed to do with this. Of course, this precise way of this precise action of BC star on the stack is the one considered by Joyce in his
yes, that's what I meant. Yeah,
right.
But he did not he is able to get something like just lattice algebras because he only used cohomologies and no potential.
Right.
Yeah, so.
I think yeah, I think seriously thinking about, I mean, this action and the associated coaction, probably would lead you to the definition of a vertex algebra without knowing the definition of a vertex algebra. It's one of those things.
Yeah. It would be sort of a right generalization of Joyce to the case of quivers potential.
Yeah, I believe so, right.
Yeah, it would be great, because I'm kind of disappointed with this absence of potential in his.
Yeah, it does. It seems like a shame, given how many nice algebras appear as cohas of quivers with potential.
Okay, maybe some other people want to any other questions? Maybe Zhou, no. Because it's a lot of algebra here. It's kind of.
I know.
Yes.
It's not my usual.
Yeah. By the way, kind of two things. So this is an example of like quiver with 3 loops. So it's simplest possible local Calabi-Yau, which is C cube.
Yeah.
And there was this paper of Kapranov and Vasserot about CoHAs of surfaces,
right,
which supposed to replace this CoHA of pre-projective algebra, which Schiffamnn and Vasserot. And so what about corresponding local Calabi-Yau threefold? So what's a BPS Lie algebra for it?
So it depends on what the local threefold is. So if you start with a K3 surface or a CY2 variety.
It might be even funner, but I take the total something for which two-dimensional kind of two-dimensional story is understand, because K3 it's a bit complicated.
K3 I think is, I mean, I think is increasingly well understood. So I should say this, I mean, this is really the content of a paper that should appear. It was meant to appear 2 weeks ago, but should appear quite soon. So for K3, the BPS Lie algebra is a Borchard's Lie algebra, so a generalized Kac-Moody Lie algebra.
Okay, great. Because you know that the origin of this idea of BPS algebra, it's Harvey and Moore, and
yes.
That's exactly the example which they wanted.
Really?
I think they predicted that it should be. I forgot. You should look at this paper of 96. Yeah.
Okay, I will, and I'll try again to re-extract a statement like that. But yeah, the answer is that you have 3 different types of roots. So one corresponding to I always get this wrong. So strictly negative Mukai vector. I want to say that. No, strictly positive Mukai vector corresponds to real simple roots. So something that generates something that looks like.
Yes, the square equal minus. Okay.
Yeah, if the Mukai vector is 0, then you're looking at something like points, and so you get there that the BPS Lie algebra is abelian, or that corresponding part of the BPS Lie algebra is abelian. So in generalized Kac-Moody terms, those are isotropic imaginary roots. And then for the general case, so strictly negative Mukai vector, the generators there are given by the intersection cohomology of the coarse moduli spaces of coherent sheaves. And yeah, for them, there are no relations. So you end up with something that's quite close to being a free algebra. And in fact, if you fix a slope, fix a polarization, and fix a what do I want to say? Yeah, a ray through the space of possible Chern classes, such that only strictly negative Mukai vectors appear, then the BPS Lie algebra corresponding to that CoHA is indeed a free Lie algebra generated by intersection cohomology
Mhm.
moduli spaces.
Mm.
So we can say some fairly precise things about what the BPS Lie algebra gives for those local surfaces.
Okay, good. And you say that it will appear soon?
Yes, yes.
Yeah,
I mean,
okay.
my co-authors are professionally interested in the appearance of this paper, so it will.
Okay, yes.
Yeah.
So I understand. By the way, you somehow said that this affine Yangian, well, it kind of was defined in terms of generators and relations. It's kind of pure formal dry style, and now it's kind of more geometric meaning. There are also these shifted Yangians. Yeah.
Right.
Some of them are related to non-compact Calabi-Yau threefolds,
Right.
but I don't know sort of a general how to derive them from CoHA, for example.
Yeah. So my hazy understanding of the kind of origins of shifted Yangians is the following. If you take the Hilbert scheme of points on C3 with its vanishing cycle cohomology, there is the usual action of the CoHA on that by raising operators, which you wrote a paper about, yeah, so this is possible to write down. But sitting inside that CoHA, you have one half of this. This is one half of the affine Yangian, and so one might ask, well, we know that for Hilbert C2, it's usual cohomology. That this representation extends to a full representation of the full quantum group. Do we have the same bit of luck for Hilbert C3? I think the answer is no, and the shifted Yangian appears when you try as hard as you can to make the answer yes. That was my origin story for shifted Yangians without any algebra.
Yeah, I understand. Yeah, I have kind of slightly maybe perpendicular point of view, but it's a different story. It's from this affine slices and the affine Grassmannian, so it's not really cool. Okay, maybe let's ask people again. So are there any further questions to Ben? All right, and I understand that at least part of that story is already in the archive. There is your paper.
I think everything in this talk, apart from the co-product with Kinjo, is on the archive. But then, because in this talk I've only considered the case of the one loop quiver, this will be the same co-product as appears in the Schiffamnn and Vasserot paper, for example. So everything in this talk is on the archive.
Okay, great. So those who kind of will try to understand better can read this paper, which is more or less the same title as.
Yeah, and it's written to be friendly. So yeah, hopefully it is.
Okay, if there are no more questions, Ben, thank you very much. Very, very interesting.
Thanks again for the invitation.
Yeah.
And see you soon, maybe.
Yeah.